All right, so while we let some people filter in, 9 a.m. is always tough for everyone, including me. I'll just explain what this funny list is on the board. Given that some lecturers that I have heard have said some things about the physics they work on has been discovered, like the Higgs, the physics that they work on is definitely been observed, like dark matter, I couldn't resist doing a little bit of spires searching. And so what is in this list here is the number of papers in thousands that have one of these titles. Okay, over here. And so I did sort of title search for things that you know and love, some things that may or may not be true here. Oh, and I of course forgot one, namely today's lectures. And for reasons, did I spell it right? It's close enough. I spelled it right when I did the search. There are sort of some funny, interesting things. By the way, this is not ordered, so these don't necessarily correspond as you go across here. But at the end of the lecture, if you're still awake, I'll join a couple of lines and show you what that means. Yes? Say what? Anything after this. Yep. Another great thing you just learned today. So if nothing else, now you know how to search for arbitrary titles. Okay. Okay, so I think we can get started. First of all, let me just say I am absolutely delighted to be here. I have very fond memories of TASI. I was here 16 years ago as a student. Myself, along with Ian, many of the other individuals giving lectures, even at this TASI, were actually at my TASI as students. I came back in 2004 and gave lectures. Interestingly, in 2004, I was asked to give lectures on extra dimensions, when that was a topic that was sort of very hot and excited for sort of 5 years, and then it was sort of on the decline as I was giving lectures on that. And then sure enough, 9 years later, they asked me to talk about supersymmetry here at this TASI. And I'm not sure that's good for the subject. Okay. Okay. Very good. Well, I think the biggest discovery that we may have in this decade is the issue of naturalness. That is the standard model with respect to the Higgs sector natural or not? Naturalness has been one of these things that's been the guiding motivation for a lot of physics. And it's sort of remarkable that we're at this state where we have a Higgs, it's weakly coupled, has all the properties you sort of would expect from a standard model point of view, and yet we have as yet no obvious evidence for something that would resolve the naturalness with respect to the Higgs mass squared. Supersymmetry, of course, its primary motivation is to try to remove quadratic divergences. Well, in this case, with respect to the standard model, we're interested in the quadratic divergence of mh squared. There are various other motivations that people could put down, but I have to say that this one is the one that I'm most interested in. Okay. The problem with supersymmetry is what I would call the anti-motivation. That is, all of the things that would have at least naively gone along for the ride and would have led to fantastic predictions in particle physics, but predictions that don't seem to have borne fruit. One of them is, so in the, shall we say, most naive And I could be very specific about what I mean by that, but this is just motivation, so don't get too worried if you disagree with what I'm about to say right now. We can argue later. There's lots of lunchtime and hikes and beer at the end of the day and so forth. Okay. The most naive supersymmetric model would have had the Higgs mass less than the Z mass. And this has been, not only has this been dead for a while, but we now seem to observe the thing, and it certainly doesn't satisfy this criteria. It would have predicted contributions to KK bar mixing, both the real part and the imaginary part, epsilon k and delta mk, that are large, easy to observe, wonderful things, would have been a fantastic thing for experimentalists. Just didn't turn out that way. So too large. Mu to E gamma would have been observed years and years and years ago. We would see flavor violation. It would have been great. This would have been wonderful. This thing should have been observed. Protons would have been long gone from the universe. Lifetime, about a second. Well, within a couple of orders of magnitude. Doesn't really matter, does it? If SUSY were exact, another great prediction. There would be tons of particles to study. Would have been, by the way, it would have also meant radiative corrections would have been much, much easier. Okay, this whole industry of radiative corrections would have been really just knocked off quickly. It would have been great. So much for that. You know, of course, okay, we have symmetries that are broken. So maybe that was too strong. If it were broken again, quote unquote, naively, it would have led to a spectrum where if this were the fermion mass, then the scalar partners, as we'll discover today, the scalar partners would have been split in mass around the fermion, one above, one below. Another thing that would have been a great prediction would have observed the selectron before we would have observed the electron and so forth. It would have been a fantastic universe to live in. Alas, we're not in that universe. So as you can see, there's this long list, and I've only given you a few of the items here. I could keep going. This list sort of keeps on going here. There's a long list of various, shall we say, anti-motivations, and yet we still have this guy. And I would say that it's sort of the power of this problem, right? The fear with regard to this problem is the thing that remains as the main thing that's driving us to still think about supersymmetry. So when I say that naturalness is one of these fantastic things that will sort of come out in this decade, one way or another, in some sense, along with that story will be supersymmetry and will be a lot of other ideas that people have been putting forth. We're sort of right at this threshold where, you know, it's not looking good, but you never know. It might be we're just this far away, and then we'll actually begin seeing evidence of this or something like it. Okay. All right, so that's the motivation. Yep. I have a point of view of gauge coupling unification, which I didn't say. I can reveal that later. Maybe over beer. It's not going to serve any role in these lectures. Yeah.
So when you say these designs we go through, why do we expect, so each reactor we have two scale requirements, why do we expect one to be necessarily better?
You'll see. That will require me, I have to delay the answer to that until tomorrow. Tomorrow I'll answer that in detail. So this is why motivation means I'm not explaining anything. Yeah. Now, okay. Any other motivational questions, comments, criticisms? Okay. Very good. So, on we go to So I have good news and bad news for you. The good news is my lectures are split over 1 week and the next week, so that gives you 2 days to recover. Okay. The bad news is that this week's topics are going to be primarily the nitty-gritty. So that means there's going to be lots of indices and twos and root twos, and hopefully I get them right. And if I don't, I can find a reference that will get them right. But I'm going to do this and sort of go from the very beginning because, well, some of you may already have a lot of experience in this area, and this will seem sort of, old stuff to you. For others, it might be you've never seen this before at all. And sort of in fairness, to make sure that everyone's on board with the lectures as directed by my dear organizers, I start at the beginning. Okay. So consider a multiplet of two particles, a complex scalar, and a two-component Weyl fermion. A free theory involving these two particles is just having written this, several things are sort of clear. One is, this sign means that I'm in I didn't hear any groans. Fantastic. Okay. That's the first thing. The second thing is that you can see that this is a Weyl fermion in the left-handed basis. This is in the right-handed, if you like. Okay, with a dagger. So this is consistent with Schrodnicki's quantum field theory book, as is this metric, and also consistent with a wonderful set of lectures and notes and the fact that I have that number memorized tells you something about its importance, by the way. Okay. I'm terrible about memorizing things. Okay, so happily, and in fact, partly because I cheated and used Steve Martin to be able to help me prepare these lectures, all of the notation will be consistent with him, including the metric and the choice of this basis. That means that when you go and look at this, it will look just like you were seeing it happen. Okay. All right, so there's a couple of preliminaries out of the way. So we would like to do, or introduce, a supersymmetric transformation on the fields. So a transformation would take the form for the scalar as something like that. This is a shift of the fermion in some way, sorry, a shift of the complex scalar, and in such a way that this variation of the scalar field, this small infinitesimal supersymmetric transformation takes this form, where the epsilon is a, let me get the precise sort of statement about this, infinitesimal anti-commuting file fermion parameterizing SUSY transformation. In these lectures, the epsilons are constants. So that means d mu epsilon is 0. And now to be a little bit more explicit, this blob here is a two-component fermion contracted with another two-component fermion. So let's expand that out. This means epsilon alpha, phi alpha. These are two-component objects, so they have these dotted and undotted indices. Undotted indices for left-handed fermions, dotted for right. The usual contraction, meaning upper, lower, gives me a 1. If I flip it, I get a sign, and all of these good things. And if any of this is mysterious, there is a brief review of it in here and much more of it in the QFT lectures of Trinity. Okay. So this is our transformation. It's constant. You can see already one simple thing, which is that since this Lagrangian here has mass dimension 4, then if I do a shift of a mass dimension 1 field in this form, then of course the shift in this phi has mass dimension of 1. So let me say, I don't know how to write this. Mass dimension 1. Okay. Then obviously, which then tells you because of the mass dimension of the fermion. So we have these objects that carry this negative mass dimension. That's fine. That's just how it'll be. Okay, so then if we do this transformation on the scalar field, what do we get? Well, let's do it. So I carry out this transformation on the kinetic term. And what I'll get back is, well, the thing that I start with. Okay, so minus epsilon dagger d mu oh, by the way, if there are ever, as you can tell, my handwriting is marginal, but I make the best of it. So if that's ever interfering with anything that you're seeing, by all means, jump in, ask me. So this is a result of doing this transformation on one and the other field, where now, of course, d phi went over to epsilon psi, so d phi star goes to this guy. Okay. So obviously on doing this so-called transformation, this supersymmetric transformation where a scalar gets rotated ever so slightly into a fermion, we have, right, a bunch of extra terms. So the only way this can make sense is if those extra terms with the epsilon are somehow canceled by something that happens on the transformation of the fermion. So we do that. So we look at the fermion and see what we can do with it. Okay. What could we do with the fermion? So your first guess might be, well, we had epsilon phi, so let's guess that this goes over into epsilon epsilon phi. Well, the first obvious problem with this is that the dimensions don't work out, right? Because this is dimension 3/2, dimension 1, dimension -1/2. The whole thing is -1/2. Obviously, this doesn't work. You notice here that upon doing this transformation, we ended up with two derivatives, one on the scalar and one on the fermion. So that suggests that then this transformation has to have a derivative somewhere. Obviously, we can't just put in a derivative without contracting it with something else. And this is one of the invariants, right, that we can write down. And then after this, it's a matter of figuring out how I'm going to contract everything. Now, here we had the scalar go over to a scalar and the scalar complex conjugated go over into the fermion dagger and the epsilon dagger. So if we do a shift of the fermion, we're going to be left with a fermion dagger here, which means that motivates that there has to be a epsilon here, and it has to be daggered. Now we can check again the dimensions of this. So we've got a scalar, y1 scalar, again, linear in how these transformations go over, y1 power of epsilon, linear in the transformation. The sigma, and then after this, it's just a matter of getting the coefficient right. Right? And the coefficient happens to be minus I. If I do the same thing with phi dagger, and I'll just write it out, it is I epsilon sigma mu d mu phi star. So this is a two-component object. This is just a scalar. This is this, whatever you call it, the invariant that's constructed from the contracting the 1/2 and the left and the right-handed representations together, giving me, so this has an alpha alpha dot, this has an alpha alpha dot. This guy's got an alpha, so this whole thing has an alpha. This thing has an alpha dot, just to get the spinor indices straight. So then if we carry out these transformations on the kinetic term of the fermion, let's do it here. We get minus epsilon sigma sigma bar mu nu d nu mu epsilon dagger d mu d nu. Where we've taken this guy on one, this on the other, carried it out. Okay. At this point, then, it doesn't immediately look like what we have over there, but we can do some contractions, shift the derivatives around, and let me not bore you with those details. You can convince yourself then that this set of terms then exactly cancels this set of terms. If you don't believe me, it's a great exercise. Turn the crank, see how it goes. Okay. So what we have then is proposals for how fields how a complex scalar and a Weyl fermion field could transform in one another, and this would allow the Lagrangian to be invariant. Good question. Coming there. Yeah. You can then do one more statement, which is after you do these transformations, you can do it again and see whether you get back to where you started from. That is, whether the algebra closes. So you can again carry out epsilon 2, epsilon 1 now, acting on the scalar. So this is the commutator of two supersymmetric transformations. You go and do it. So epsilon 2, epsilon 1, epsilon 1, epsilon 2. And then what's going to happen is, well, you take one of these, you hit it on the scalar, it'll shift to a fermion. Take the other one, you hit it on the fermion, it goes back to a scalar. And if you work out what that is, it is okay, so it goes over to then this derivative acting on the scalar field. You could do the same thing for the fermion. This is what it'll look like. Okay. So, two supersymmetry transformations acting successively rotate into the fermion, rotate back, or rotate from a fermion to a scalar and back to a fermion, and then we're left with this derivative. So already this is sort of an amusing state of affairs in that we seem to get back something that then corresponds to, well, a derivative in momentum space is like the momentum operator. Right. This is sort of what's already telling you that there's a connection, right, between what a supersymmetric transformation would do and that it is somehow directly related to Lorentz transformations. Now, your question. Everything I did here was, quote unquote, on shell, whereby the equations of motion for the scalar and the fermion were satisfied. Now, for the fermion, the equation of motion for a two-component fermion is that. And of course, those of you who are more familiar with the Dirac equation, you take this guy, you take the sigma bar, and then you take the sigma, and you group it together in a gamma matrix, and you contract it through, and that's the thing you're used to seeing. Okay, so here's what it looks like. The thing that is, yeah, so on shell. Right. Okay. We can go off shell, but then it turns out that we need an additional field to soak up degrees of freedom. Now, how we see that is that a scalar, whether it's a complex scalar, whether it's on shell or off shell, has 2 degrees of freedom, a real part and an imaginary part. A fermion, on the other hand, this two-component fermion, has 2 components, each of which are complex. This equation has, if you like, you can convince yourself, eliminates 2 degrees of freedom from being dynamical degrees of freedom in the sense that they, you do a commutator and blah, 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 and you figure out whether these things should be quantized. That's a good exercise, by the way. Let me be precise about what I mean by that. So you can verify that if you go off shell, so on shell, there are 2 propagating degrees of freedom, and off shell, there are 4. So it's interesting to sort of take this, the equation of motion, and to convince yourself what is it, how does this actually operationally show you that some of the degrees of freedom are not propagating on shell. Yeah, massless, yeah, no mass terms. Yeah, good, yeah.
So, have you used the on-shell condition yet?
You bear with me, yeah? Let me step through the auxiliary field and then you'll see. Yep. Okay. So the curious thing then is that I do this supersymmetry transformation and I get back, I start with 2 scalar degrees of freedom and I have 2 propagating degrees of freedom for the fermion, and that's fine. If I go off shell, seemingly I have this mismatch in the total number of degrees of freedom, right? There's 4 for the off-shell fermion and only 2 for the complex scalar, which is telling you that there's something missing, right, in the formalism to be able to handle this if I have a general theory of the particles. So for that, we need to introduce. Where do I want to do this? Hang on, one moment. I've run out of blackboard, so. Yeah. This doesn't move, right? Okay. I'm going to remember that. Anything I don't want to discuss, I'm going to put on the board behind. That way I can cover it up quickly. All right. So this issue with on-shell, off-shell is analogous to what happens to a gauge field, to which you are all familiar, in that there again, on-shell, you have 2 propagating degrees of freedom, the 2 polarizations. Off-shell, if you look at the kinetic term, expand this out, you have a d mu, a nu, d nu, a mu. You can get my nu and mu's straight, but you already know what this is. If I pick out the 0th component, zeroth component here, then the antisymmetry of this tells me that I only have that. Did I do this right? Well, okay, you get the idea. Let me say this differently. This vanishes. Namely, that there is no time derivative of the 0th component, which is telling you it's not a dynamical degree of freedom. And so you don't integrate over it, for example, in the path integral. This is sort of like an auxiliary field. In supersymmetry, we also can introduce an auxiliary field. And like this guy, it is going to have no kinetic terms at all. So L auxiliary is something then that has no kinetic terms. The auxiliary field is usually given the name F, and it is complex, and that is its Lagrangian. No kinetic terms. Means if I do equation of motion, so on shell, it vanishes, right? On shell, on shell. we can handle these degrees of freedom by doing a modification of the supersymmetry transformations that we wrote over there. And the modification is that, that we have df goes over into minus I epsilon dagger bar mu d mu phi. So you see this is sigma bar d mu phi. This is, right, what would otherwise have been the equation of motion for the fermion. So now, off shell, this doesn't vanish, nor does this. That's the linkage. Okay. So now if I take right. So then dl, a supersymmetry transformation of this auxiliary Lagrangian, goes over into mu d mu phi f star d mu phi dagger d bar mu epsilon f. So this is sort of a strange state of affairs. We take the equation of motion, we have that the transformation of df corresponds to that. We do a supersymmetry transformation, we end up with more terms. But here's the trick. Now, if we do one modification of something that's on the board underneath, I think, yeah, here. If we do one modification to these equations, namely that we add epsilon alpha f and whatever the Hermitian conjugate would be, I think, then these additional pieces, when contracted through on our original kinetic terms, will then cancel this guy and that guy. So we have then the ability of doing the supersymmetry transformation on the field, both on shell, where df is just 0, or off shell, where then this fermion equation of motion, the additional degrees of freedom there, are soaked up, if you like, by the f. Now, a couple of comments, if I'm going to cover this up again. Lagrangian, don't ask me why I kept doing that. I'm surprised someone didn't jump in and say that, but anyway. All right. Lagrangian action. Very good. So, who's awake in this class anyway? All right, no, I'm sorry. Clearly I'm not. Say what? Huh? Ah, fantastic, yeah. So that's right. This is really an S. And then my Lagrangian is, fantastic, is L. So this is what I screwed up. All right. Very good. I probably won't keep that notation. It happens. What can I say? Obviously, the dimension of this, 4, the dimension of this, 4, which tells you the dimension of F is 2. And we know it's complex because we know it had to absorb 2 degrees of freedom. Well, we know because I got an F star, so, but, you know. All right. So now this whole degree of freedom matching works off shell. Okay. I have to erase. Now's your chance to bug me. So I have a feeling Tom is part of designing this blackboard, since even at my height, I still can't reach the top when it's at the very bottom. That is great. Oh, look at that. Experienced lecturer. All right. All right. So we have the transformations. Now we can construct from this various bits that will be useful as we proceed further. So if we have then a transformation where we do one rotation of a field into another, and the Lagrangian is invariant under it, it is a symmetry, it is supersymmetry. That is what supersymmetry is, at least with respect to Weyl fermion and a scalar. Any symmetry that a Lagrangian respects has a conserved current. As Noether taught us about 100 years ago. And in this case, it is what is known as a supercurrent. Supercurrent satisfies d mu, j, mu, alpha is 0 and the daggered. Right. Anytime we have a conserved current, we can construct charges out of that. Q, alpha, E3x, J, 0, alpha. Let's define the other one. So here are our, oh, I already did it. Here are our charges associated with this conserved current. For various conventional reasons, there are root 2's. They're of no consequence to how this is just a matter of definition. So with these conserved charges, then you can go use the infinitesimal supersymmetry parameters, epsilon, epsilon prime. You can turn the crank on them and take from here, from these conserved charges, and then go and construct what the corresponding operators, if I promote these to quantum mechanical operators on the Hilbert space, what they would then correspond to. This is definitely you can follow it right in Steve Martin if you're so inclined, or you can sort of walk yourself through it. But when you do that, given these conserved, given these charges promoted to operators, you end up with this sort of famous result. Let me get all my bars straight. Okay. So the operators corresponding to these charges, doing an anti-commutator of the two objects, giving me back the momentum operator here. This is not surprising because when we did those supersymmetry transformations once and twice, we got back the derivative of the field. The derivative of the field, which is, right, just the Fourier transform of what this thing would be. The 2 is conventional, hence the root 2. The sign, it corresponds to making a choice of metric and also a particular choice of the sigma basis. Shall I say the rational choice for the sigma basis. And yeah, there it is. But this is really just sort of, this is a good sort of exercise. You can then also convince yourself that Q with P mu compute, and the dot, the other guy, commute. So this computation tells you then that, for example, if I have some in-state, some field, and I operate on it with, say, P, and let's go into the rest frame, P0, right? This would give me back, well, if it's a massive field, and let me not get into all the difference massless map. This would give me back that. So since these guys commute, this tells you then that no matter what if this thing is supersymmetric, then operating on this with some supersymmetric combination gives me again the supersymmetric combination with the same mass. How do you want to say this? The mass is m of equal. Yeah, I'm somewhat being quick when I say this, but what I really mean by that is if I act on an object which itself has a supersymmetry transformation among its components, then all of those components will have the same mass. Yes. 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 Yeah. Meaning, yeah, this will force that upon you. So if you set different masses, you will find that then you do the SUSY transformation, and it won't work unless the masses are equal. Another great exercise. Okay. Very good. Yes. Probably. Yeah. I mean, this way of, if it's true in one frame, then I can do a boost and then, it follows. So it's happily, we're not imagining that supersymmetry is also breaking Lorentz invariance. So we can keep that. In fact, to my knowledge, that was once an interesting possibility whether you could have a model which would be supersymmetric and SUSY would be broken dynamically, and then whether Lorentz symmetry would also be dynamically broken. And I don't know that anyone ever showed that you could do that. I do know who tried. And all right. So now what? So all of what I've done so far has been with respect to just a Weyl fermion and a complex scalar. And if we start adding more fields, how do we do this? We have to do it the way we usually do this thing. Is you add some other field, you have to do a SUSY transformation, transform it, see what happens, go back, and it just gets painful. Right? So then if you start writing down Lagrangians, that's fine. You don't have to, you can do this, but then you'll have to explicitly verify that supersymmetry transformations go through and the Lagrangian is supersymmetric. It would be nice, somewhat like the mu nu notation for f mu nu, and so forth, to have a manifestly supersymmetric notation for this, where we don't have to check the SUSY transformations every time we write something down. And that's really the origin of superspace. So it is the formalism that allows us to have manifest supersymmetry. Colloquially, we can think of this as something where we have space-time in some direction, and then we're going to have new quantum dimensions, as they're sometimes called, corresponding to these generators of the supersymmetry transformations. It's connected to space-time because of, right, these relations up there. So, superspace, then, of course, what I should have done here is put the generators for this and not the coordinates, but all right, anyway. Fine. So, superspace will be, the formalism will be something that then involves coordinates in this space, x mu, and coordinates in this space, which I'm going to write as theta alpha dot dagger. Now again, there is, you will commonly see this written as a theta bar in literature. In keeping with tracking something through where you can open up a Steve Martin note and just see what's going on, I'm going to stick with his notation with a dagger, but it's just notation. If you don't like it, you can go and change it back. So with this in mind, we have 4 of these, so we have coordinates of 4 scalar degrees of freedom, and then we have alpha 1 and 2, alpha dot 1 and 2, or 1 dot and 2 dot. And these are complex degrees of freedom, so we have in total 4. Here. These are coordinates, as you can expect, because they come from generators that are anti-commuting, are themselves anti-commuting parameters. So that leads to all sorts of amusements, and you know, it's one of those things that I think you sort of run through this a bit and eventually you get used to it. And then it just sort of looks normal, and the first time you see it, you look, this looks crazy. But that's sort of the nature of superspace. With these coordinates, then we can write out what a general field would be with respect to various powers of these coordinates. And a general field that is an expansion in powers of these coordinates is called a superfield. A general superfield would be one in which it depends on all possible combinations of these coordinates. Now, the interesting thing about these anti-commuting coordinates is that as I try to multiply more and more of them, eventually multiplying them out, they have to vanish, simply because if I have theta alpha, right, and I write this thing out, theta alpha, theta beta, plus theta beta, and so forth. So if they're anti-commuting, then this thing, vanishing, will then tell me that various combinations of these will also vanish. In particular, I will only end up being able to have one coordinate, so call it theta 1, in this S expansion. Now, the way this is usually done is to not isolate individual components here, or otherwise we're really doing something funny about picking the SU2 cross SU2 part of the Lorentz group. So you normally do it in terms of the two-component guys, but then the way to make a theta-theta allowed still and allow it to be anti-commuting is to have another anti-commuting object, something like epsilon. So what I can imagine doing in this expansion is having some field, let me write it as, say, A, with no dependence on any of the thetas, and then I can begin expanding this out in terms of powers of different combinations of thetas. So I can have a theta alpha some field. Let me just be a little bit careful about what choice I use for the field. Use Xc. Okay, and so then this corresponds to theta 1, Xc1, theta 2, Xc2, and if you like, these are the coordinates and then these are the parameters, as they will turn out to be the component fields of the expansion. So we have that. We have the daggered guy, which is alpha dot, chi alpha dot. And then we get into these various combinations. So this combination that I've written here, alpha, epsilon, alpha, beta, theta alpha, this combination here is usually then just written as theta theta, or even theta squared. But by that, this is just a very simplified notation of writing out this combination, a combination which, because of the epsilon, means that I'm never contracting a theta 1 with a theta 1. So I do that, and then I can keep on expanding the superfield, theta, theta, say B. There's then theta dagger, oh, let's guess C. And then a theta dagger, sigma bar, mu, theta V mu. And let's keep going. Theta dagger, theta dagger, theta, eta, theta dagger. And last but not least, I think I got them all. No, I didn't. Yes, I did. No, I didn't. Yes, I did. Yeah. Sorry, say again. Ah, good. Yes, there is such a term. You manipulate it, it comes back into this term. Moreover, there are other things that you could have imagined that might have been invariants in here, and again, you can transform them and convince yourself that this is the invariant set that we have. Okay. With this in mind, now you can start doing degree of freedom. Oh, sorry. What about keep on going? So if I could try to write a theta cubed, what would that be? Well, theta cubed would have to be then theta with one of these indices, theta with one of these indices, and another theta with another index. And all of them have to be different indices because it's anti-commuting. But this exhausts itself after 1 and 2, so that tells you that this vanishes. Similarly, theta dagger cubed also vanishes. So this is it. The expansion in terms of the superspace coordinates exhausts itself at this term here, this theta, theta, theta dagger, for a general superfield. Yes? So you want to do 2 sigmas in the last line. Here and here. Ah, yes. You can do that as well and manipulate it. Comes back into this set of terms. Yep. It's the joy of 2-component spinor magic, right? Fierce identities, blah 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 blah. Yep. That's what it is. And we could go into that, but this is that's field theory. You can look that up. Okay. So this is a general superfield. This is in terms of now what? What do we have here? So we have a complex scalar, a 2-component fermion. Let's count the scalars first. Complex scalar, complex scalar, complex scalar. Vector, but it's complex. A little odd, but true. Complex scalar. 1, 2, 3, 4, plus 4, 8. 8, did I count that right? I think I counted that right, yeah. 8 complex degrees of freedom, or 16 real total. Fermions. 1, 2, 3, 4, all 2-component objects. So 4 2-component fermions, 8 1-component fermions, 16 real degrees of freedom. So it matches. There's a lot of degrees of freedom in all of this stuff. And this is, of course, just one of the things that happens with general superfields. This in itself is not particularly useful, as we'll see. What will turn out to be useful will be various contractions of this guy, various simplifications of this superfield, and they can turn out to be the superfields that are actually potentially relevant to expanding out a non-supersymmetric theory and promoting it to becoming a supersymmetric theory. With this sort of, I have to cover it up. Okay. See, I'm optimistic. I'm erasing the entire board. I think I will fill it again. Okay. There are operations you can do on superfields. Super space. We can differentiate. Yeah, let me get my indices straight. You can do the same thing with the dotted indices. It'll go through. This means things like d by d theta of some contraction. For example, that contraction then becomes d by d theta beta beta That's funny. All right. Alpha. Again, just to remind ourselves about what happens when indices flip up or down. I think I did it right. This was, sorry, with a upper alpha. If you do a lower alpha, you've contracted with an epsilon. The epsilon means you'll get a sign, so you'll flip the sign. You can integrate. And the common integration measure that you'll see is d squared theta, which is now again, it has to be, so to be able to have an integration measure that doesn't just automatically vanish, it has to be contracted with an epsilon to be antisymmetric. And there is this little minus 1/4, which, whether you believe it or not, I wasted an hour verifying, okay, just for your benefit. And having gone through all of this effort to verify it, I'm not going to tell you how you verify it, but it's in my notes if you're interested. So if I do this, I get 1. This is the curious thing about superspace, is that the derivatives of theta, right, pull this down, but the integration also pulls away thetas. Differentiation, integration giving me sort of the same thing. All right, another wonderful little simple exercise. Basically just get your sines and alphas correct, and I tell you, it's almost impossible for old people like me. I guess this is what the algebra manipulation programs are really for. Okay. Good. So that's integration measure. Very good. This operation, this integration giving me 1, oh, and by the way, if I tried to do this, right, this would vanish simply because, right, there's not enough guys to come in here. Like differentiation, if this is like differentiation, then pulling away 1, I do it again, there's nothing left, so it vanishes. Similarly, if I put nothing in there, it will also vanish. Okay. So this measure, these integration measures, are extremely useful because it will be ultimately how you construct Lagrangians that are supersymmetric in terms of fields that can actually be the fields of the everyday world that we know and love. In particular, if we take the integration measure d squared theta of S, what does this do? Okay, so we integrate with respect to d squared theta of this object. This piece, gone. I hope I'm doing this right. Yeah. Now I'm suddenly, yeah, fantastic. Sorry, momentary lapse of reason. This piece, gone. This one, gone. This is gone. Integral of d squared theta, theta squared, d squared theta, theta squared, I get B. So this is my first component. Keep going into here. This thing gone. This gone. That is gone. Only one theta. Two thetas. Two thetas. So we get B, theta dagger, psi dagger, theta dagger, D. I wanted to push it down. What did I say? This was B. I've already forgotten the fermion. Psi dagger. And the last one I happen to remember. You do the same thing with the barred. Daggered, excuse me. And you get the analogous field that would be here. You get a theta with some field there. And you get theta, theta, D. So different field than B, different field there, but the same D. Okay. All right. Similarly, if I integrate d squared theta dagger, now I'm taking two theta daggers, well, I'll get back just D. Okay? All right. Happily, they've given me 6 lectures today, so I can just keep going on and on. All right. What do I want to do? So, okay. What we would like to do is then do supersymmetric transformations on these superfields and see how that carries through on the components. And if it works, what should happen is that after we do the supersymmetric transformation on the fields, or on the component fields, it should give us what we found before, just by sort of hook and crook of doing a little transformation and making sure that it goes through. To do this, well, how do we do this? This is where I'm deciding what to do and what not to do. All right, if we do it on, if we try to do a supersymmetric transformation on a superfield, then this will go through into whatever it is in terms of its components. Now, we can do we can express this supersymmetric transformation in terms of combinations of epsilon dagger plus the generators associated with the supersymmetry transformations. And those are Q alpha dot, Q dot, plus, and then there happens to be some funny sign here, some conventional root 2, which is irrelevant, and then S. And if I carry this out, I get so I get a shift of theta and theta dagger. No surprise there, because these anti-commuting little supersymmetry transformation is like doing a rotation in superspace. And then I get some additional pieces here with respect to x mu. Again, not surprising, because when we did the supersymmetry transformation, we ended up with a derivative. The derivative telling me it was something about some sort of, translation. So that's what's happening here. So this is, if you like, a translation or a rotation, depending on your point of view, in superspace. There's one more object which I have 0 minutes to discuss, but I'll do it anyway. One more object, and then I can pick this up next time. Let me just do one more little technical object. If we attempted to do a supersymmetric transformation of a derivative, do I want upper or lower? Upper, good. Of S, a general superfield, you can convince yourself that this is not a derivative of the supersymmetric transformation acting on S. This is analogous to if I do a derivative of a scalar or a fermion field that also transforms under a gauge symmetry. I don't get then doing a derivative on it and then a gauge transformation versus a gauge transformation. Blah, blah, blah. It doesn't work unless I use a covariant derivative, right? Covariant with respect to the gauge. Here, there is something analogous. There are I don't know, what's the name? I forget what the name is for these dumb things. Superspace derivatives which do satisfy this property. And essentially what they do is if I do a supersymmetry transformation, but now on d alpha S, this will go over into d alpha of S. You can do this with there is both a superspace derivative and in the left-handed part of the Lorentz group and one in the right-handed guy. So a D and a D dagger. These D's and D daggers look superficially very similar to the Q dagger and Q and Q dagger that are somewhere buried. And they look like U. Okay, and there's a daggered guy, which you could dagger probably yourself. However, as much as this looks awfully similar to the Q hat, it's not the same, and in particular, D with Q hat anti-commute. It's sort of, once this is true, once you construct something that satisfies that, then sort of this will follow. That's essentially how you construct them. So what we've got by the end of today is how does supersymmetry act on a component field, a complex scalar, two-component Weyl fermion. We have preliminarily written out what superspace does, what a general Cauchy superfield looks like, and what certain constraints, namely integrations on it, will do. We've constructed superspace derivatives, d alphas, that then respect this relation here. And then what we will be able to do tomorrow is use the d alphas to provide constraints. And they will then take us from this general superfield to particular kinds of superfields, ones that can become the ones that are the extensions of the MSSM, so the quarks and the leptons and the gauge fields and so forth. And that is where I will leave it for today.